We are on the final for the first flying JRM-01. The last parts came right out of the printer. Completely new designed inlets. They are angled and has a nice round shape. And we got the canopy, one of the last fuselage parts. The last days we did a lot of design changes on the JRM, and Mark will tell us some more details now.
For the design of our very early winglet, I worked on the basis of using narco profiles for the wings, lofting those between two profiles. So here you can see the outer profile and the inner profile, and using a guide curve along the leading edge, define that particular loft. In this instance also there was a small defect on the main surface, so I chopped that out and filled that void or that space. One of the key elements with this particular wingtip design was the trailing edge was 1 millimeter in width, so that dictated the profile tail end on the very outer wingtip area, and that resulted in a nicely transitioned wing profile. Transitioning from the simple wing profile, I created a large cut in the tail end, from which I then lofted small extension, I suppose, the finger extension of the wing, and then using the flex command twisted this up and forced this up through the flex geometry features in SolidWorks, defining the radius and the amount of flex, in this instance 90 degrees, and then trimming off the rear of the profile because I wanted it to be printable in a vertical orientation, and providing enough surface area and a nice flat level face so that that wingtip could be printed vertically, standing upwards. And again here, magnet holes and support rod protrusions or cuts to the inside face of the winglet. For the next design, I used the base model profile of the earlier smaller wingtip winglet, trimmed that off and created a whole new extrusion and extension, and then again using the flex command to flex that particular winglet upright. One of the issues with the flex tool is that it bulges out the profile in certain areas. You can see the perimeter line is relatively lumpy and not exact. It's great for quick results, but not necessarily a nice clean model. Again, this design was cut and trimmed so that it could be stood upright for printing along that bottom edge. It gives its distinct forward swooped trailing edge type style, which didn't really match the JRM model, so we've decided not to use this particular winglet. Still provided as an option, but we're not seeing this as the one that is our preference, and we're then developed further designs. In this particular winglet design, different ways of creating a more accurate outer profile of the geometry, and I was tasked with using surfaces to define the geometry of this particular winglet. We used a top view, a front view to define the direction of the winglet profile, which then allowed me to create planes and surfaces onto which to sketch a lofted surface. If I hide my extruded planes there, you can see using the sketches with our 60-degree incline to define the profile of the outer part of the winglet. Now that we found out that these winglets were printable as is, standing up without support, we continued on this idea that we could actually curve and curl the back edge or the trailing edge of the winglet. And in this instance we got this particular design but weren't happy with the rounded nature and the styling. It just didn't match our JRM model. So we opted to try another profile. To overcome the bulgy results of a flat wing that is just twisted up or flexed up using the SolidWorks flex command, I needed to generate some accurate geometry for our particular wingtip. In this instance, I opted for a blend between two profile surfaces, which I created using construction planes, and then a blend surface between those two objects or two bodies, and allowed me to create a very smooth and accurate profile of the winglet, which had the same angle as our vertical stabilizers, so it was in keeping with the form language of our jet. A result that was much cleaner and much more professional, and not just a quick rush job using the flex command in SolidWorks. The last of our profiles was the Lazy Man winglet, a very simple approach to creating a wingtip design, winglet design. This design is intended for vertical printing, so along that face here, sitting upright like so, and as you can see, a plate or a boss extruder added to the end with some radiuses added to it, and then some fillets to combine and join the parts together. So very simple but quite effective wingtip or wing-gate design that we will be using on our JRM test flights. In the process of completing our design for the JRM-01C model, Renee and I decided to work on some winglet designs for our extra large wing that we've developed for preliminary flight tests. Here the array shows a variety of wingtips that I developed for our model, starting with the preliminary basic wingtip, a small finger design wingtip, curled shark fin style wing, bit more stylish wingtip here, the grey one with rounded end, and then the more noticeable and more striking, I suppose, wing design that matches our jet and the vertical stabilizers of the JRM-01. The final wingtip design was more for fun, and we will see whether its performance is any better than any of the earlier designs shown here. One of our considerations was the exchangeability of these wingtips on the model. So Renee and I have created pockets to embed a 8mm magnet and 2 holes for our support rods of those wingtips. This should allow for fairly easy disassembly in the field and testing of each wingtip style. Leading up to our test flights, Renee and I have decided to increase some of the wing area of our first test flight jet so that we can guarantee at least some success in our first flight. So tonight we worked on a larger wing. I've overlaid the 2 designs. So from our first wing design, which included a larger tail or larger aileron section, we've now not only increased the angle of the leading edge but also extended the secondary aileron section in our print, as well as moved the tip of the wing out considerably. So in this instance here, the green wing doesn't have its wingtip attached, so you cannot really judge the change, but here you can see how much of our wing we've actually increased. So these sections here are considerable change, and then also added a very basic wingtip for first test flights. The root profile is the same on this particular design, so that we can easily interchange, again with cable management for the outer wing servo, the carbon rod support holes, and of course our magnets for attachment. So this is some of the lead up to our first flight, and the beauty of 3D printing, because we can quickly add and change the designs and modify the designs prior to flight, as well as after crashes and any damage to the aircraft. Here is a quick view of the evolution of our JRM-01 model. The JRM-01 very first design at the top in blue, our JRM-01B version, which had a centre of gravity that was a little too far back, so the nose section was stretched to create our JRM-01C. The B model here has the winglets of our most recent design attach them because it shares the same wings as our C model. As you can see, a lot of the features have been taken over from our predecessor, which was the JRM-01. Some work happened here in the front area of the cockpit, cleaner cockpit, nicer lines. That seam line running through to the nose was accentuated on our B and C model. On the C model, the nose extension increased our front strakes here, so this area here has been stretched forward, and we have also increased the distance from the main vertical VTOL thrusts towards the third jet, which is sitting under the cover here, for our front ducted fan. All in all, we're very happy with the way the design has progressed. It's, in our opinion, looking better and better as we're getting closer to our final design and closer to our first flight tests.
Lot of new parts, let's assemble them. Here's good visible where we saved a lot of weight. We widened this compartment a lot, also there. So we got more room for all the electronics, flight controller and so on, and also it's much more lightweight. It's time to paint the canopy. Here this nice gold color, let's see how this works. First I'm checking the color. Yeah, it's golden. Maybe it should be a bit more sanded right before. Let's see. Time to remove the masking tape. The next parts are done. Inner ailerons, vertical stabilizers, outer ailerons. And the advantage of these big printers is a whole wing, 2 parts can be printed at once without changing. And the new long winglets are printed. Even this big overhang is no problem for lightweight PLA and the Ender Pro, super nice. And here's the wingtip. It's a bit Airbus style, the upper and lower, just the fans. While building the JRM and making it ready for the first test flight, we also work on the print profiles for the Bamboo Lab. Here for instance this little hatch for the battery cover, and let's take a look what we did. Now you see it is absolutely clean from the surface, nothing to see. And when I choose here on the upper, the original Bamboo Lab 0.4 nozzle, let's take what we see there. And you see we got all these small slopes outside. This would be failures on the surface. With our new print profile we could remove them. Let's go back. And you see no slopes at all. Okay, let's go to the printer. This part is printed with lightweight PLA from ColorFab. Great. Here it is. It's not a big part, but the quality is what we are looking for, and this looks really good. No failures in the surface. Also a good bed adhesion. Yes, very good for lightweight PLA. Meanwhile, the last wingtip is printing, and that's the place for this little part. It's a battery cover, and we installed up here, make it a bit wider for better grip. And this goes on the JRM-01. Here's all the technique we will install in the first prototype. The receiver, telemetry, the gyro, speed sensor, the speed probe itself, the capacity sensor, BEC, 2 satellite receivers and 2 batteries, one with 4200 amps, one with 3000, both 5S. But at first we will remove a lot, the legs and everything that is not needed to make this jet as lightweight as possible. So let's go. And also the front door fan servo can be removed. The main engines are fixed in horizontal position. So, elevator and nozzles are running. This time they are coupled because I need the extra channels for the big ailerons. They will run as flaperons. But nevertheless, I think this will work very nice. And also yaw, vector and rudder are coupled and run nicely. So, es geht voran. Speed probe is installed, speed sensor, cable, telemetry. Then we got one satellite receiver, gyro, receiver, telemetry module, and the second satellite receiver. So everything is installed. I also did the first programming. Here we can see the ailerons are working as flaperons. So they are flaps and ailerons, and they are coupled with the droop nose. When I take off the winglet, we can see this is how I want to generate much more lift to make the upper surface as curved as possible. Also, the vectors are running smooth. But anyhow, after these late night install work nights, everything looks like a mess. So time to clean up and go on. So workspace is cleaned up again. So we can go on with the jet. Everything is installed. And at first, let's take a look in the setup and the programming on the TX. We got a wing here, and the wing should work with two flaperons. This means ail and flaps mixed, because we just have two servos to save weight, and they should work as ails and flaps. So battery is on, and when I give ail, you can see they go synchron, the ailerons and the elevators. When I just give elevator, it looks like this. Rudder is also coupled with the nozzles. And now this is the ailerons as flaperons. They go down, but they appeared a problem. When you take a look at here, you see this looks really not good, because somehow the TX is doing something strange. Let's take a look in the menu to Klappen system. This is meant for the system of the flaperons. So, and here we see us. We got the 3-step switch with the 3 positions. This 76 is the maximum down, and this 25 is the middle position, and this is 0. And Höhe, German word for elevator, there's always a 0. So normally there should move quite nothing, but it moves, and this will not work. I can't figure out what's wrong here. The latest software version is installed, everything checked. Ask my buddies who also deal with this DXX18. No idea what to do. So that's quite a pity, because these ailerons can't use as flaperons, would be one idea. Other idea would be that I just couple the elevators and don't use them as tailerons. Now this works, no problem. But when I fly very slow, I don't have these tailerons for help to stabilize on the roll axis, so it's also not perfect. And the next problem is that the gyro just stabilize. Wait, you can see this better. So now it's better visible. When I move the jet and the gyro should stabilize on roll axis, we see that just the ailerons are moving, and normally the elevator should also move as tailerons, but they don't. They just move normally as elevators, and the rudders as well. So we got two problems. The mixing problem, This caused by the TX while bringing the flaperons down, that there appears something strange on the elevators, and the gyro doesn't support the ailerons. So what to do? So here we got plan B. This is a new TX FR-Sky X20S. Because this one is now about 12 years old, and I think this is overloaded with all my wishes on the JRM-01. And this got also much more functions. For instance, the receiver got a gyro inbuilt and also the whole telemetry, while we needed here extra gyro, quite heavy, extra telemetry module. So this is much more up to date, will save a lot of weight, but this thing is completely different.
Willkommen bei Ethos. Gasknüppel nicht in Leerlaufstellung.
Okay.
Achtung, kein Failsafe eingestellt.
Okay, no problem. This is absolutely different to set up. So this will take some time to dive deep, especially with my special wishes. All these mixes has to be done also here. Think it's possible. Tomorrow I will visit my buddy Tommy. He is very good in programming this TX, and we will figure out if we bring this to work. But nevertheless, in the meantime, I will do some thrust testing. Here we got a horizontal inlet, nice curved, then an angled inlet with a bit flat on the inlet area, and the new designed angled inlet, nice and round. And let's see what generates most of the thrust, because the estimated takeoff weight of this jet will be around 1.8, 1.9 kilogram. Depends on the batteries on these two. And we need as much thrust as possible, minimum 1.5. And let's see where we could generate the most. Looks super beautiful with these winglets. And here the last wings are printed. You can see this is a Kitty X3 Max. It's printing with the maximum power. This means 30mm print speed, 12,000mm acceleration. And here's the X Plus, printing the other wing side with the same settings. Just the temperature. Here I got 246 and here 248. Normally I print with 240, but caused by the higher speed, to get the same result and the same foaming, I set up the temperature a bit higher. And this works really well. Before the thrust test will start, I will add these capacitors to the ESCs. They were not included in the set, otherwise I would have done this in the first place for sure. They go there. I think it's possible, something like this. Let's go. And here they are. Minus on minus. This looks good. Getting ready for the final thrust test. Here we got the batteries. They will be used for the maiden flight. 4.2 amps and 3 amps. 5S each. Here we got the inlets. The angled ones. Both. One has a bit straight surface. This is nice and curved. And this is the flat inlet. Looks not so cool, but maybe gives more thrust. And they will be installed with these carbon tubes. Fits nice and clean. So everything is in place. And then okay, it's not bad. From the smaller battery, we got our 1.5 kilograms thrust, and max was 84 amps, but then 76. This is good. And next are the angled ones with the nice smooth curved inlet. And we start again with the smaller battery. I would say there's minimum loss, minimum less, but also the battery gets a bit empty. So they work quite good. And at last we take a look at these. We are not so optimal from aerodynamic view. Let's see if this has some circumstances. With the angled ones with the flat inlet surface. They work very good. I didn't thought that they work so good. They're just a bit better than the other ones. This is the battery with the lower C rate, and they also made 1.5 kilograms at 72 amps. This is quite good. The ESCs stay cool enough. I can touch them, no problem. I also cut a little hole in the string tube that there could be some air circulation. The next version will also have a hole underneath the ESC that the air will push out all around, because it's also getting high on the lower side. So we will use them for the maiden flight. 1.5 kilogram is really good. So I'm super surprised with the test results. I thought that this one will be the best and this second, but it came on a very other way. It's done. After some hours of programming with my buddy Tommy, it is made on this new TX on the FR Sky, and we got the ailerons moving coupled with the elevators and working as normal elevators. And also the gyro function is completely included, everything just with the receiver. Let's shake here, we can see stabilization on the rudders, elevators, and elevators as well. And everything is controlled by this 3-step switch. And this also controls the droop nose. So we can see how this works. And also this is for fast speed, and on fast speed there are no ailerons included, because there is enough authority by the ailerons itself. And when I go for normal flight, then we got the ailerons, and on super slow flight as well. Maybe this is a little bit too much deflection, but this we will figure out tomorrow. The important thing is that it works, and also the telemetry. We take a look at here on the airspeed. We got the airspeed. This works also super nice. And then some questions to the FR Sky community. Do you got any idea how to bring this data, for instance the airspeed and also the battery capacity and whatever telemetry data, bring it as a video file out? At the moment I have to install this extra camera here. This will film the display, and I will mix it into the video to show you while flying the actual airspeed, but it's super complicated, and I know it from Yeti. On Yeti it's possible to bring this data, the airspeed and so on, into a video file. If somebody got an idea how to do this, let me know in the comments. This would be super nice. The new receiver is installed. It's much more clean inside this compartment. And also, super important, this area is free. This will be needed for the flight controller or on the VTOL version. And let's take a look how much weight was saved. So 0, just the new receiver. Weight 30.3 grams. And this is the old technique. Gyro, satellite receivers, telemetry module receiver. So let's take a look. 74 grams. So 60 grams. Over 60 grams we saved by the new technique. Super cool. While the fuselage is almost ready, the next chapter are the wings. The wings are super important for this jet. We need a lot of lift and also nice handling and super acrobatic ability. A lot of wishes for the wings. There are different constructions and also different wing tips or winglets. Yeah, we take some time for some designs to check out how it will fit. These are some small wing tip, curved wing tip, bigger one, and also these Airbus style wing fans to upper and lower side, and then just straight normal wing tips or just a cut off. And also the wings itself are different. We enlarged the aileron. It is much bigger. Here's the original size. When we compare this On the root we added, I think, 50 millimeter or 10, and on the outside 5. So it was hardly enlarged to get more aileron momentum and also more flap area. Then we got the droop nose as usual, and this wing is without droop nose because I want to see if the droop nose does a good job at all, or can we get rid of them, because this is also a lot of weight, because the servo and the cabling. And at last the whole wing was enlarged, and we compare them here. You can see this. There we can see this. This is on this area where these parts are divided is 3 centimeter more or 30 millimeter more. So it's a lot of wing area more. And also the wingspan is higher when we put on the wingtip. This is just a prototype, so no winglet is on it. But you see, all this is necessary because of the big wing load. And the big wing load is, because of all this technique. At the moment, the jet will weigh at about 1,900 grams. We will check this just before flight. But with the VTOL technique, there will be added about 300 grams more. And it's super important that the slow flight ability of the jet is very handsome, that there won't be any stalls or anything while the transition, and also the acrobatic abilities shouldn't be too much disturbed by this high wing load. So the only thing we can do is enlarge the wing area to bring the wing load down, because we did everything we could do to make it lightweight as possible. There is nothing more that could be done to save any weight, and so we have to work on the wings, and let's see how they look like. Now on one side is the smallest wing and the biggest version. Here we see how this looks. I think this is still a nice shape, even if this is the short version of the fuselage. Meanwhile, we did make the fuselage longer in this area because we got a CG problem. So this whole area has to move forward, that the battery can move forward, that the CG fits without any trim lead. And with this longer fuselage, I think this bigger wing also will look super nice. This is just if we got problems with the other wings, then this will be installed. So that's why flight test is super important. And I would say, let's take a look on the flight test program. And here's everything that will be tested tomorrow. The JRM with the big wings. Let's have a look. What is the final weight? The empty jet with no battery, 1,374. And the lighter one, 422. Okay, that's not bad. I thought it was about 1,800, and we stay a bit low. I think this is because of the change from the new receiver. That's not bad. We got 1,500 gram thrust, so nearly about 1-to-1. So, and with the more heavy battery, almost exactly on the 1,800. That's really not bad. When we remember, the VTOL technique is 370 grams. So the final VTOL jet will weigh about 2,200. Let's say 2,200. It's not bad. Maybe we need these big wings, we will see, or maybe the smaller ones. So let's talk about the test flight procedure. And here we got the test flight plan. We will start with the big wings, because I think this will be as easy to fly. And the first stage is figuring out the CG. So let's see what we want to do on our test flight procedure. At first, the important thing is figuring out the CG. The CG is where all the lift comes together. This should be around here in the rotating axle of the sweepable nozzles. And this will be done in horizontal flight with power and without. And when the power is shut off, the plane should go slightly down and glide. And there shouldn't be any nose up or nose down tendencies, even in fast flight. In fast flight, it should stay on the horizon. Then we got a nice CG. And the next thing is figuring out the deflection of all our rudders. This means that the jet feels nice and handsome while flying, especially while flying turns. It should make a clean movement, not just roll. It also should rotate on your axis, that clean turns are possible to fly, and that we have all the time enough control over the airplane, maybe when the nose is more up or more down, but it shouldn't be too much that the whole plane is not easy to control. Yeah, this is also right after the CG. This is the most important thing on the flight test. Then the next thing is figuring out the stall speed. The stall speed is important on every airplane, just to know which number it is. And for this plane especially, because the transition between vertical takeoff and horizontal flight and the way back, from horizontal flight to vertical landing, there we go through the minimum speed and go below it. And the behavior of the jet from normal lift to stall is super important to know. The plane should be controllable as long as possible. That's why we got these big rudders, big elevators, big ailerons, and also the mix with the ailerons. Also the rudder itself are quite big and have big deflections to keep the jet under control as long as possible. Yeah, and super interesting. With the Harrier, I think we reached about 35 km/h, but this was with the help of these removable nozzles. Let's see if this is possible with this jet also. We got more wing, lower wing load, and the whole fuselage creates also lift. So this is more or less whole flying wing. And we want to see when it stalls, what happened, because it shouldn't start spinning on its own. Spinning should be an acrobatic figure, which is forced by the rudders or ailerons, but when it goes under the stall speed, it should just suck down something like this and sink vertically. There shouldn't be any tendencies of spinning. This would make the transition extremely worse. So the jet should be controllable and handsome even on stall. So the next point is the maximum horizontal speed. For sure, we must know how fast this jet is, always super interesting. That's why we got our speed probe in here. And also for the CG and for the trimming, it's super important because even on maximum horizontal speed, there shouldn't be any nose down or nose up tendencies. So, and next point is starting with the acrobatics. This means starting with standard acrobatics like looping, rolls and sharp turns. Turn is also an important figure because most accidents and incidents happen while stalling in a turn. This means in this, then the inner wing stalls and the plane just starts spinning. And this should not happen. Now we got a backward swept wing. This is on this wing it's more dangerous that the inward wing or inbound wing starts stalling. On this forward swept airplane there was the opposite. Even when you turn like this, the outer wing stalls, so it flips in the other direction. So this time we focus more to the inner direction. And here the most important thing are the vertical fins. They keep the jet in position and they are not that big, so it could be when there should be this tendency for stalling that here has to be added some underneath fins, also like it was done in the SUX, or these vertical fins has to be sized up. But this we want to figure out. So, and after these normal acrobatics, it goes on with inverted acrobatic. So this way. And here it's again important to see if the CG is correct, because we want to have the same behavior. This means in horizontal flight, it shouldn't be necessary to push or pull the stick. The jet should be very harmonic and stay on the horizon. The SUX does a very good job on this. A bit nose up, because the airfoil is not that curved on the lower side, so for the same lift we need a bit nose up, but at the end it should fly super nice and smooth. And also here we want to know the stall characteristics. What happened when we reach stall speed? Does it start spinning, or does it stay and just sink down? This is super important to know your jet. And then the next thing is advanced acrobatics. This means everything with flying behind stall. So snap roll, this means very fast pull elevator, then happens like this. It is fast moving around. This is not easy to fly, but all the time the jet should be controllable. Yeah, this is the important thing. And also what I wrote down here, Culbit. Yeah, this is one of my most loved figures. This means a very steep and very tight looping. Yeah, it's just a roll along the lateral axis. This is just possible with this vector thrust nozzles, because we are at a very low speed and also want to have a very high rotation rate. And also the Culbit and the Cobra maneuver. The Cobra maneuver is one of, looks very easy. Just pull nose up, stay for a short moment in the air, and then accelerate again. But it's not even that easy, because you need a really good feeling for your elevator and also for your thrust. Even when you're in this position, you have to accelerate your engines, and the gyro must be capable of holding the jet in this position under control. Yeah, it should look like this. And right after the flight test with the big wing is done, the same will be done with the smaller wings, but with no droop nose. And at last, the wings with the droop nose will be tested to see if there is really an advantage from these droop nose, have more lift, slower minimum speed, and also better handling. And at the last point, also these winglets will be installed to see how they help to give the jet a better slow flight behavior, because these are changeable. We got two types I will test, and these big winglets, I think they even look really nice, so it would be super interesting how the jet performs with them. Yeah, and then everything is done and we know which wing will perform best. We know our speeds. Then it's time to start the real VTOL thing. So I hope you enjoyed the video, and we're all looking forward for the test flights. I think maybe tomorrow they will be done. Yeah, the weather outside in Germany is really getting cold. And if you like the project, you will find some links underneath in the video description where you can support the channel. You can become my Patreon. There we will post a lot of behind the scenes photo, or can donate on PayPal or buy me a coffee. This would be really appreciated. And I would say we see us in the next video with the result of these test flights of the amazing JRM-01. So have a great day and bye bye.